Hello, my name is Daniel Yates of Pitt State University in Kansas. I am a polymer chemist major, and I'm giving a presentation on the big three: chain entanglement, summation of intermolecular forces, and timescale of motion. Now, these are very important to understand if you're going into medicine of any kind, or if you want to preempt problems and solve them ahead of time in creation of any type of polymer. Now, the first thing we're going to do is chain entanglement. This is a very complicated subject, but as you can see, all the different twists and bends and colors and just massive array of arrangements that they can come into. But these are proteins, and proteins are part of a polymer, and they behave very, very similar to a polymer. This is actually how polymers might actually fold up, but a protein isn't a polymer of your own DNA strand. And so this is very important, but very complicated. We're going to start understanding them by understanding the intermolecular forces. Now, these are in order of magnitude on their bonding, on the intensity of their bonding. Ion dipoles, hydrogen bonding, dipole-dipoles, and London dispersion forces. Now, your ion dipole, you can see the ions, the anion and cation are negatives and positives, and they are very huge in their magnetic force. And so when you have a dipole, of which is a force of negative and positive on opposite ends, like the North Pole, South Pole, you can see how it would be attracted to it by the opposite side. And it makes for a very strong bond. Now we have hydrogen bonding. As you can see, this graph is of boiling points on group 4 of the periodic tables, and you can see a steady incline of the temperature. But when you add in group 5, 6, and 7, you can see outliers on the first row on each of those. So the H2O, HF, and NH3 are the main ones we talk about when we're talking about hydrogen bonding. And they're very important because temperature is very important to the twisting and bonding of things. Now you have the dipole, which just attracts the opposite dipole, the opposite end of a dipole. Now, your London dispersion is very weak because it doesn't last for very long. As you can see, the electrons will move, and they might accidentally make a huge negative on one side of the dipole. Now, this will attract your positive, but since those electrons still move, it will actually forfeit that bond. And so over time, we will see this dispersion. Now we are focusing in on the University of Maryland's mathematics for a two-state folds in time. Now, our two-state fold equation, W is between 3.8 and 4.2, N, lowercase n, is viscosity, A is the length, Y is an average surface tension, and capital N is the number of amino acids. F theta is dependent on theta. Theta is dependent on temperature. Temperature initial minus temperature final over temperature initial creates our theta, and theta gets plugged into it. Now this is a very simple equation. I could go into much more complicated ones, but if you want to do that, I would recommend chain dimensions of entangled spacings. Chapter 10 of the Physical Properties of Polymers Handbook in Penn State University. Now this will go over tubing, how the actual polymers will actually bend, and they will only address into tubing. You can do math on this where it has a backbone or it doesn't have a backbone. So this is very important for medical stuff. And this will actually help you understand the way the DNA strand comes together. But very complicated math. Now we have my cited. Thank you for your time.